Hello guys, I'm making this video to tell you what I've been doing in the meantime while I'm not making tutorials for you. And I've been studying currently computer games engineering masters in Newcastle University. And what we've been working on is creating and developing our own game engine. Well, it might sound too big to be true, and it sort of is, but what we've been making is we've been working on low-level graphics such as OpenGL and its exposed language, GLSL, to create graphical representation of whatever we would like to show to our viewer. And this current engine that I've developed myself based on the NCL framework, the minimal one, this engine is able to load up OBJ modules and extrude them, tessellate them, make them take textures, and display the model in the space. And I've chosen for my model a planet which is hovering in space and is hopefully looking like some sort of ice ball. You know, it's full of craters, you can see shadows and deviations of the surface, you can see reflections everywhere, and all of that is completely different to what we've been doing in Unity, what I've been showing to you previously. All of my 9 tutorials where I show how to create a horror game, this is different to that thing, because this is low-level graphics and it's built on C++. Well, let's go part by part on what you can see in this scene. Currently I have a skybox all around, similar to the one that you could see in any game engine, in Unity for example. This one is a cube map with 6 textures, which are lining up and you can't see any seams of it. This cube map was taken from the Space Engine. Try it out because it's an amazing approximation of our universe. You can check it out on Google. Just Google Space Engine. And well, this is a cube map all around, you can see. The planet is reflecting the cube map via the shader that I wrote. Well, we're writing all the shaders, we're creating all the transformation matrices to make sure that our planet shows up on the screen where it's supposed to be. So when I'm rotating camera, I'm really adjusting the view matrix of the camera, which is being supplied to the shader, excuse me. And it's pretty much all of the matrices, the view matrix that is relevant to our camera, the transformation, the modal matrix that brings the planet where it should be in relation to other objects. For example, it's satellite, which is somewhere around here, I think. It's spinning around the planet, and its world matrix, the modal matrix, is constantly changing. So I'm using all of this information to provide data to my shaders. I compile all the shader objects, fuse them into same shader program, link it up and use it in OpenGL via C++. My shader also supports basic reflection, which takes and samples the cube map all around us that you can see here. It samples it in all of the pixels and all of the fragments and outputs the reflection, for example the reflection of this galaxy. You can see a couple of seams here, and that's because of the way I've unwrapped my OBJ model, which was loaded up into this engine. The engine once again is built on a basic framework, which is the NCL framework. It provides just basic functionality already. Well, I would be able to write something like this, however people that have been working in Newcastle University made sure that it's optimized, and it provides me a couple of matrix manipulations and multiplications. It provides me vector operations such as cross product, dot product, and so on. And everything else I have to code up myself. The planet also utilizes refraction, which you can see on its edges as it refracts a couple of things on the borders. Refraction, reflection. It also has bump mapping, which I had quite a lot of fun with when I've tried to come up with TBN matrix, which takes your vector from the world space and puts it in the space of the texture so that you can sample normal maps, and that's really how everything works in all the game engines when you work with normal maps, for example in Unity. Well, yes, so we got bump map here. We also got specular highlight from our light right there. You can see it as a white glare on the top of the planet. reflection from the stars as well, and I also extrude my surface based on the height map texture, the black and white one. As you can see, my model is not very highly subdivided and not tessellating right now. That's something I'd like to work and improve in this framework later, in this engine. But we do distort the model based on the height map, on what it already has, on what vertices it already has. For example, in this crater, those elevations where the height map is white, we push the vertices outwards, creating the distortion, because this model of the sphere was a pure mathematical geosphere. So it had perfect round edges. As soon as we apply the height map to it by my engine, it distorts, and we send this vertices information directly in the shader, apply all the matrices there, but we don't perform tessellation on the planet yet. This is something to be done in the next step. Also, quite possibly I might implement parallax occlusion mapping here, which is going to be quite interesting to see, but yeah, this is sort of similar to normal mapping that I already have here. Also, I would like to show you that I've got transparent objects in my scene, and I've got how it's called, the point light implemented to almost good ability to shade objects all around, because it has a cube shadow map. I've got some awful shadow acne here, which I'm currently battling, and that's because the resolution of my shadow map, which is used to shade the planet and everything around the scene from this point light, this texture is low resolution. So I might increase it, or I might do something with implementing in C++ my own shadow cascades, but this is something different story. But because I have transparent objects, I'm also ordering my geometry, because as you know, or as you might want to know, different type of geometry, transparent and opaque, like my planet is, they have to be drawn in strict order. Opaque objects first, and then transparent after the opaque ones were drawn. But I do all of that. Yeah, there is some nasty acne going on here right now, which I tried to fix, by the way, with Peter Panning, which I did fix on the planet, but they are of different scale, so I'm having trouble with the different scale of objects. And this is just one side of it. This is just graphics. Another part is the physics module, which can be plugged into the game engine to work and position objects, allow them to collide with themselves. And this is something I'd like to show you in a second. Of course, a very important part of the game engine would be sound, as well as networking for a proper game engine. But right now I've got those two big modules, physics, which I'll show you in a second, and this graphics. As you can see with this satellite that's orbiting, and currently you can see the shadow from the TARDIS being applied to the satellite. But this object is orbiting around the planet, and its world matrix, as I said before, changes constantly. This is a so-called scene graph hierarchy, where this object perceives this big planet as its parent. So if I would suddenly decide to move and change the world matrix, the model matrix of this big planet, the satellite would move with it as well. Don't be surprised or don't be laughing at the decision that I made about the seams. This is some sort of, extraterrestrial spaceship, big spaceship which is made by aliens, as you want to say. But in reality, this is just how I've unwrapped my geosphere, and there were some ugly seams which I've decided to just hide away by shading up my geometry where the seams would lie, so the seams just don't show up, or they show up in a very funny way, like this big golf ball or whatever. So I've tried to play around, and I think I've succeeded with playing around with Fresnel effect, where I take a look at the incident vector, how my view vector is falling onto the surface, and based on that I shade my model, I play around with refraction and reflection. For example, the planet is not reflecting anything if we look straight into it, but it goes and reflects everything on the sides, and refraction is also only showing on the sides of the planet, where we can see steep at a steep angle towards the surface. But when we look straight into it, the incident vector is perpendicular to the surface normal, which is resulting in different stuff being outputted to the screen. I also play around with MIP maps and different resolution of the same texture. For example, to sample the reflection from my cube map, and applying this reflection would create some very sharp, ugly looking reflections. So instead, I create reflections on my planet based on sampling the information from the lower MIP map of the cube map, which means that I just basically take the lower resolution of the cube map of the sky and sample this low resolution, which allows me to create smoother reflections on the surface of the planet in my shader. TARDIS didn't receive too much attention from me, although it's there, and it has some bump mapping which you don't really see here because of the awful shadow acne that I have. I think my shadow map is about 1000 by 1000, 1024 by 1024 resolution. It's not very high resolution, it's not being interpolated, so we've still got some basic phone shading. We've got diffuse, we've got specular, we've got ambient as well. And finally, if I decide to check out what's inside of the planet, I simply don't allow the user to do that. As soon as we dive into the planet, a quick post-processing effect just draws black stuff on our screen after everything has been drawn to it. Otherwise, we would see culled things, because I'm doing backface culling in my game engine. You are not able to see the object when looking from behind of it. It culls everything. And also, I'm implementing the frustum culling. As soon as I move my camera away, the TARDIS will not be passed to the graphics card for drawing. But as soon as its bounding box enters, or part of it enters my screen space or camera frustum, is going to be sent off as the entire object to the GPU. Using its own shader, the TARDIS shader, it will compute all the shadows, all the diffuse and specular, which will result in this object right in front of us. I think I'm done with graphics, and I would like to show you one more cool thing that I've done, the physics, which was quite difficult to implement, and I'm still not 100% sure with it. It uses a couple of interesting things. Let me first of all turn on my project. Let me first of all turn on the module of this game engine. There it is in all of its glory. You can see that we've got rotating objects, such as the same TARDIS we saw in the previous scene, but this time it's rotating. And I forgot to mention that the engine is built based on the glue and GLFW, which allows me to create the context for the window, create the window itself, and allows my program to work and output data to the window of Windows operating system. So this module doesn't have anything fancy, it just has got some basic primitives, but its main focus is on physics. This physics is not PhysX, or not Bullet or Havoc physics packages that people have been working on for ages. This one implements some basic Newtonian linear motion and angular one as well, based on formulas, and a couple of interesting things such as manifolds, and it resolves collisions based on contact points, all of which I detect myself. So without further ado, let's show around what I have here. Currently we got scene hierarchy, scene graph hierarchy, where objects are parented to each other, and each object has some sort of approximation of the collider shapes all around it. This means that graphical representation of the objects can be completely different from the physical one. The physical one is usually more simplified, and in my case it's using convex shapes, the ones that are not bent inwards, like boxes or spheres. So currently, if I press Q, I'll throw in cubes, which we can stick into the TARDIS. And by the way, you can see, well, I think you know what this is because of my tutorials. This is a octree. So we try to subdivide objects into different regions, and as soon as we can't split our octree into smaller nodes, because we've reached the depth limit, we're just gonna highlight them with red. And yeah, I'm rebuilding my octree every single frame because it turns out that it's the best solution for me right now. and I send objects once every single frame into their nodes and build the octree over and over again, disposing of it at the end of each frame, at the end of each physics update. My physics runs about 4 times quicker than the graphics, and the engine runs at, well, too many frames actually. Without physics it runs about 300, 400 frames a second, maybe even higher, especially on my ice planet. Here you can see that I've implemented the objects, and you can see the green ones are the ones that are currently actively being checked with physics upon. The red ones are which falling asleep. They are not being calculated by physics unless they get a collision with something. Yes, so physics engine is pretty much an entity which looks at the velocities and the forces being applied to the objects, applies constraints to them via some very scary things like Jacobian matrices and stuff, which I'm still learning about a lot. And it resolves all the forces into a single force, integrates it into the velocity, integrates the velocity into, actually integrates the force into acceleration, acceleration into velocity, and then velocity into the position of the object. Repositions all the objects, and then performs a second iteration of the physics update. It happens about 4 to 8 times until we finally refined all of the with all of the iterations our physics things, and we are able and are allowed to output the correct representation of our physics results via the graphics module, so that it's drawn on the screen as a frame. So for every single graphics frame there's about 4 to 8 physics updates going on constantly. I'm not also bounded by the cubes. For example, I can spawn more cubes here, and I think the splitting limit is about 10 objects per node, maybe slightly more. I'm not just bound by the cubes, I can spawn spheres and tetrahedrons. Spheres, I think, are with J button. They're rotating and we're taking away energy from the system, and they stop rolling and fall asleep as soon as their velocity or change in position, I think. I don't remember. As soon as it's low enough to indicate that the object has fallen asleep. But there was a funny thing, because as soon as we throw an object upwards, it would get stuck in the air because it would reach its top of the arc, because it would, you know, switch direction. It would hang there for a split second. So instead we see the position changes within a period of time. This means that as soon as I throw my object up, as soon as it's coming to rest, we start our timer. And if it would be staying at rest for, like, you know, 2 milliseconds or maybe 30 milliseconds, then we put it to sleep. So that's a good way to do it. And because each object has got an inertia matrix, this is some sort of very heavy computation which is just blowing my mind. So I've used the inertia matrix of a sphere for the tetrahedron. And as you can see, it's thinking that it's actually a sphere, and it orients the object in this direction because it thinks that it's the best way it can position the object. So yeah, it just thinks that it's a sphere, but it's kind of good. It's okay. Even though it has got just 4 points, it doesn't have a radius like a sphere does, it still uses this inertia matrix because inertia depends on the mass distribution across the object. So how much the mass is distributed across the volume of the object. If we supply the inertia matrix of a sphere to the cube, it will also behave in a very strange way. But yeah, that's what we currently have here. Another thing which I've been doing in my physics engine and had lots of fun because I love trees, I've built a KD tree. The KD tree is a k-dimensional tree. If I press B, you can see that we have much less nodes, but the tree is dynamic. So the way it's working is it's also sorting objects by position, just like the octree, except that the octree always splits the node around the middle of the node, around its center. The KD tree doesn't split itself into 8 children like octree does around the center, but it splits itself into 2 nodes, the positive one and the negative one. And the plane where it splits itself into 2 nodes is the mean or the average of a position of the objects. The way we split the big node is first we split it in X, and then the further two children, if needed, they split in Y, and their children will split in Z, and the children of those children will split over again into X. So it constantly goes X, Y, Z, X, Y, Z, always putting the splitting plane on the average position of the contained items of this node. It might sound complicated, but if you've watched tutorial number 9 of my videos, it's a piece of cake for you, hopefully. So yeah, we can see this flickering that's occurring here is because of the Z fighting in the graphics that I've implemented for this physics engine. Z fighting means that the objects are kind of overlapping on the Z buffer. So our Z buffer thinks that one of the objects at the current fragment is actually closer than the previous one, and its neighbor fragment is thinking completely the opposite thing. So the object flickers on the screen. This can be fixed by reducing the view distance of the camera, so that we give ourselves more iterations for the Z buffer, but it's not a big deal right now. The good thing is that I've got the physics and the graphics module running for this game engine, and there is a, you know, completely separate game engine from what I've been using right now. As far as you know, I've had 6.5 years with 3ds Max. Well, to be fair, 5 intense years with 3ds Max, all of which you can see in my series of tutorials that I've been outputting. This is a cool thing that I'm really enjoying. I'm enjoying my course right now. If I spawn more objects, for example somewhere on the right here, let's say cubes, as you can see, because we're putting the means, putting the splitting planes on the means, you can see that the tree dynamically adjusts itself, and because it's rebuilt every single frame, what you can see is that the splitting planes are being dynamically adjusted and dynamically chosen for the objects. Also, a cool thing about this KD tree is that if the objects of any given node are lying in the same dimension, for example currently we're looking in Y dimension, the nodes would want to subdivide in X, Y, Z, X, Y, Z, X, Y, Z, and so on, until it either has reached the depth limit or it has got few enough items in a given node. But if we would allow it to subdivide in Y, then we would have to put both objects into the top node and in the bottom one. And because they're lying on the same Y coordinate, really, they're all lying on the floor, this would mean that almost all of them would make their way into the bottom one and in the top one, because they would have to be included there. The mean in the Y coordinate would be lying directly through the cubes. So the way I do this is, when the need comes to subdivide in any given dimension, Y, X, or Z, if it lies too close to those borderlines, then we deduce that the resulting two children nodes would be very thin, and instead we block the opportunity for us to subdivide in this dimension, and we try to subdivide in the following dimension. For example, if Y fails, we would try to subdivide in Z, and if Z would be too thin as well, we would try to subdivide in X. If all of them fail, fine, we are no longer subdividing and this node is done. Let's process other ones. But if we can still subdivide, then the further children are passed a reference to the vector, which has 1 for each component, where 1 means that the node and its children are no longer able to subdivide further in the given dimension. For example, if we put the vector with 1, 1, 0, this means that every child of this node would no longer be able to subdivide in X or Y, but potentially in Z. So we save ourselves computational time on that. I'm also doing the OMP, using the OMP library and functionality to thread out any kind of for loops that I'm using, but of course only doing this where it's applicable, where objects will not be interacting and items won't be interacting with other branches of OMP. So using some sort of managed threading, not a very difficult one. But I do this for every single node when I have to find the mean. This is a completely separate operation. I can do it on a separate thread, no problem. So I thread out all the finding of the average of X, Y, or Z component. And that's working out very nicely. If you have got 4-core processor or 8-core processor, it just flies very quickly. So all of you can see here is me debugging some important information. So yeah, I've showed you the Oct tree and the KT tree. The KT tree works very nicely if the objects are spread enough, because otherwise the nodes are becoming too thin, which I try to combat with, as I told before, once again, by not allowing the tree to split if it's too thin, instead attempting to subdivide in the further dimensions. The Oct tree works very nicely if the objects are packed together. So even though it's wasting some cells and they're completely empty, it's able to refine down the particular nodes such that you get a better distribution of items per nodes. But with this version of KT tree, it's not too bad either. And the purpose of the Oct tree and the purpose of my KT tree is that this physics engine works in really 2 stages. It works in the broad phase and the narrow phase. Because I have so many objects here, and let's say I've got 3,000 of objects all around, which I'm not going to be spawning right now, but it's possible to make. If I would have that many objects, you know, it comes down to the problem of n² complexity, because for every single object you have to calculate if it's colliding with anything else in the scene. This has been discussed somewhere in the middle of tutorial number 9 of how to make a horror game tutorial. Check it out, it's quite interesting. This way we are partitioning out our items in this game engine into separate nodes. We are creating pairs, which is pretty much just breaking down the big n² problem into smaller n² problems. But that way, for example, we know that in this big node there are only 2 items, this and this, so it's just a single pair, and we are reducing our computational necessity by a big amount. We definitely know that those cubes won't be intersecting with anything here because they are in different nodes. In the broad phase, quickly discard any collisions that are not possible. Then I do a cheap sphere-sphere check, because I'm comparing against the positions of the objects and the radiuses of their bounding spheres to see if any collisions are possible or not. For example, here probably the sphere-sphere check returned false. But if the objects are close enough, even in this case, for example, like those tetrahedrons, then this pair is saved into an unordered map, I think, and then it's sent off into the most expensive check, the stage, the narrow phase stage. In the narrow phase, I make use of the SAT, the separating axis theorem, where I try to find the face of any of the 2 objects within the pair, which would allow me to use its normal to put a plane in between of 2 objects. And if I can put a plane in between of 2 objects without this plane intersecting any of them, this means that the objects are not intersecting, as long as their hulls, which we're testing with, are convex. So if we could put a plane in between of them, then it's working properly. However, this, as you can see, is called the narrow phase, the most expensive one, because the objects can have more complex convex hull representations with more vertices. So much more data has to be computed against. The set is quite expensive because we are taking a normal of the object and are projecting with dot products the hull in a given dimension, trying to find the overlap. Well, just look up SAT, separating axis theorem, and you'll figure out for yourself. You can see and examine the overlaps of the projections of their hulls on a given dimension to detect if the items are intersecting or not. And as soon as we detect that they are in fact intersecting, which happens quite a few times, for example here, they were intersecting for a split second, but then they got pushed apart. As soon as we detect that they are intersecting, we try to figure out what the penetration depth is, what are the collision contact points, what is the collision normal, to be able to estimate the direction in which we should push the objects apart. And of course, their mass and their current velocity plays a big role in it, because if you have a huge object with a big mass and large velocity colliding with a small object with a small velocity, then the bigger one will experience almost no change and the smaller one should bounce off vigorously. And in reality what's happening is the objects that are colliding are constantly intersecting with each other. And because the physics engine is running, many times in comparison to the graphics updates, we are able to push objects apart and actually kick them off, set them flying according to the physics rules before we actually see this on the screen. So we immediately, as soon as we detect that they are overlapping, we separate them and then we apply the forces, change the position based on the mass and velocity appropriately. We also set the spin to the objects if needed, and this is done via the Jacobian and the constraints. Because objects might be overlapping in various ways, where there might be several contact points, we try to predict how the objects would be touching if they were not intersecting, if they just began to intersect. We try to predict those and estimate those contact points, and we use them to apply the forces correctly to the objects. Because it might, the two cubes, for example, when intersecting, when colliding together, they might have hit each other with an edge towards the face. So the edge, the entire edge would serve to us as the basis for applying the forces and would affect the rotation of the objects accordingly. So this pretty much covers all the engine as far as I can see. We try to refine everything in the broad phase, and then process everything that's indefinite and might very likely to be intersect in the narrow phase. I've talked about the scenes update, the physics update as well. Well, I tried out and I support about 1000 of items at a time with my KD tree and Occ tree. And yeah, that's about it. Thank you for following me. Thank you for being subscribed. I think I might, if I have time, give you a tutorial, which would be an epic tutorial about shaders in Unity. However, right now my main interest is about mastering the C++ and learning how to make and engineer game engines. As you can see, I've advanced quite a bit. So thank you very much, guys. I hope to see you in the future.